did we want to wait a little bit more? Did we want to get started? I know that people are trickling in. I can
Oh,
see that.
yeah, I guess we can just get started since
Okay.
we'll have lots of people here.
Okay. Awesome. Thank you. Um, all right. So I'll kick us off, and then I want to quickly throw it over to Professor Ye. Hey everybody, my name is Zan. I work at Together, um, and I'm really looking forward to learning about GPUs from Professor Ye today. Just before we begin, I wanted to tell everybody a little bit about what Together AI is. Together AI is essentially an AI native cloud. We specialize in training, building, and running Gen AI models, everything from large language models to text to video models, text to image models, diffusion models. Um, and we're working with a lot of the AI native companies that you hear about and powering their models. One of the reasons why I like to really work at Together is because I get to learn from leaders in the field every day, right? So people like Percy, whose courses I've taken on Stanford Online, Tree, the experts up and down the stack from GPU kernels to fine tuning to inference, training. So this is kind of why I really enjoy working here. Um, and we really do cover everything up and down the stack, right? So if you want access to some GPUs for an hour, we have the GPU cluster product here. If you want access to models like Kimi K2, Kimi just recently released another model. Um, Access to the best open source models through an API. We provide inference on 200 plus leading models. And then if you want to take those open models and fine tune them on your own data set, we have our fine tuning API. We have dedicated compute where you can deploy your models and only your traffic will go to it. And for companies that want to build their own models from scratch, we provide them the infrastructure to do that as well, right? And of course, we kind of serve pretty much companies that are up and down the stack, companies that are trying to build their own models, companies that are trying to fine-tune open source models to serve their purpose, and companies that just need lots and lots of compute, need access to GPUs. Um, and so this is why we thought it would be a great idea to partner with Tom, teach people about GPUs, and I'm really looking forward to learning from Tom as well. So. Uh, with that, please take it away. Thank you so much.
Uh, Hey, Zane, thank you for the introduction, and I'd like to thank our sponsor, Together AI, again for making these educational experiences that are available for a lot of people. And it's a big crowd, and it's also a very technical topic. And I'm trying to break it down using the AI by hand method. Hopefully, go through this Excel that I shared with you. It's lots of blank. We'll fill it out together with pun intended. Um, and then I'm also because I thought that we might have question in the chat, so I also brought in Shanya. Shanya, do you want to say a few words? She's my former student and she worked at Micron and she knows a lot about GPU memory as well. So do you want to introduce yourself real quick, Shanya?
For sure. Thank you so much, Dr. Ye. Hi, everyone. My name is Shania, and as Dr. Ye said, I was his former student in his computer vision class at CU Boulder. And now I work in ecosystem development at Micron, so making sure that the GPU memory subsystem does not have any compatibility issues when our product reaches our customers. So that's my current role at Micron, and I'm really excited to answer any questions that any of you might have.
Yeah, so please ask your question in the chat. I'll be helped with Zhang and Shanya between them that we should be able to address most of your question in the background. And so just make sure you know where the chat is. I'm going to like to you to tell me if you've been to a lecture like or an event run by us before. Can you type one in the chat? If it's your first time, can you type two? So lots of ones. Thank you. Good seeing you. And lots of two as well. Welcome. Hopefully you like this learning opportunity and learning style. And then you go. So let's just gonna go share my screen now. Am I already sharing my screen? No. Okay. So this is my screen. So I want you to think of it not just an Excel, but you're seeing a really big whiteboard. I'm going to sketch, compute, and calculate and explain, and as if you're in the classroom. And okay, so the really big whiteboard, and then you also have your copy of this. If you go to this link, you can grab a copy of this, and you could follow along, or you could just look at this, and with your recording, you can follow along. So I want it to be an experience that you'll be taking down notes as well. Then you should learn this by hand. All right. So today we talk about GPU. I would like to start by tell you why and why GPUs, and that with graphic and also transformer model and all the fancy AI stuff you have. And then getting deeper and deeper to show you like some basic of what does it mean by running many computation at the same time using different threads. What does it mean by warp? And then talk about the kind of nitty-gritty detail about how we could save memory using quantization. If I heard the word quantization, I want to show you how it can be done mathematically in a very accessible way. And so at the end, I want to show you how some of the design of GPU can be influenced by, let me just not annotate this. How do I, okay, erase, okay. Okay, and the design influenced by the advances in AI. Okay, so let's just start now. And okay, let me see. Okay, all right. So first, let's talk about GPU. So the G is stand for graphic. When the GPU was made, there was intention. It was completely different. Nobody actually thought about building this for AI. And then the GPU took on its life for in the crypto, and then now AI. But let's go back to the basic graphic. So I prepared a little example to show you that how GPU could be used for computer graphic. So I draw this little shape. That's, you can think of it as lots of points. This is a point cloud, and I build a little rocket here. In computer graphic, you would like to transform this rocket so it can move in different direction, or you can move camera, can see that rotate and it'll become bigger and smaller as well. And so the way you can do it is actually, turns out you can do it through a matrix multiplication. So something that you hate when you took linear algebra, but then you start to appreciate once you are working in the real, like Intel, NVIDIA, and so on. So I want to prove to you that we can use matrix multiplication. So I've used the Excel building formula mmult, and to take one matrix, this is my transformation matrix, and also take in all the coordinate of these points with extra one. And then one is a trick for you to do translation. So now nothing, you don't see any changes because this is, if you remember your math, it's an identity matrix, so nothing changed. But let's see what's going. If I add a little 0.5 to my first letter, you're gonna see that, hey, it's actually scaling along the X direction. If I change 1.5, another one is scaling in the Y direction. If I put one and put one here, it's kind of shifting around. If I put a little bit here, and kind of turning into one direction. Do you see all this? And this can be all done by this matrix multiplying with all these points at the same time. And one thing about matrix multiplication is that, well, it sounds very complicated, but it turns out there's a fancy way of saying, hey, I'm doing a lot of dot products. Okay, so let's see, dot products. Okay. Anyway, I think there's some chat, but I think Zhang and Shania is helping me taking care of the chat, so I'm gonna focus on this here. So I want to show you that product, like what's going on here. And so if I turn it back to 2 and 1, so it's just a little easier to manage. So, and it turns out like this point, if you take any point, this point is a result of taking a dot product of these three number and a dot product of these three number. Okay, so and then how to compute dot product is you take 4 and 2 together, you get 8, and 0 and 3 together, you get 0, because 0 times 3 is 0, and 0 and 1 together, you get 0. And when you add them up together, you get 8. Okay, so you do this all at every single location. And then once you see this, you realize, hey, it's very easy to parallelize it because it's just doing exact the same computation over and over and over again, but at a different offset of your these matrices and numbers. So that is there's an intuition behind a GPU that allow us to parallelize this dot product over many threads. I can do it a lot faster. Simple computation. And let's jump like 20 years to maybe 10 years, 15 years to the 2017 when the transformer paper came around. So I did a lecture before to show you how you can grow a neural network all the way to transformer by hand a while ago. There's a link there. You can go if you want to review that. But today is just to show you that this is a self-attention computation, and that but the key is not to teach you this, is for to show you there's a lot of matrix multiplication. So we have 5 tokens here, and then all representing as a series of numbers. And if we want to compute key, so all we do is actually matrix multiplication. Take this weight matrix and also take these tokens, and it'll turn them into a smaller number of keys. And this key is going to be compared to, queries. These are query vectors. And do another matrix multiplication again. This is the third matrix multiplication I implemented today. So this is another matrix multiplication here, okay? And then if I move all my keys here and all my query here and take a lot of dot products, so that's when we get this attention score matrix. And then we take some kind of, this is called softmax, to turn that into probability value. You can see this is actually between 0 and 1. Eventually, I take my value here, do one more matrix multiplication, and then I can do this. And then, so they become attention weighted tokens. So I'll just very quick review in just 2 minutes. But again, the point is not like really how self-attention works. To show you that I just did 3 matrix multiplication. So there's actually more here. This is another matrix multiplication. Another matrix. So it's a lot of matrix multiplication. And this attention matrix is something get bigger when the context window get bigger. The query, more and more query, more and more keys. All right. So what I got interested in is I gonna just delete this equation, just redo this again. But I want to show you that this is where we compare this query and this key. And what we do is actually dot products. So this is the first test I have for everybody in the audience, that what is the dot product of this value? What is the value of this dot product? If you can type in the chat. Okay, so we have 19 from, 19 from Rodrigo, and 19 from Vikas, and Namra is 90. I guess you meant 19, right? It's a typo. Anyway, so 3 of you, thank you for participating. Please email me afterward for get a special gift, and between AI by hand and Together AI, we'll figure we'll want to send a special gift for participation. Okay. Anyway, so this is 19 here. Okay. So that erase all this and put 19 here. And just to make sure, so this is like to prove that it's actually matrix multiplication, is I just do matrix multiplication of these 2. Okay. And get 19 over here. And if you get a bit more technical, in the transformer paper, they have this like scaling factor. So I'm just gonna add a scaling factor just so that I'm not misleading you. I do a square root of the dimension of a key, dimension 2. So this is in the transformer paper. So you're done. I bring the attention back. Okay. So anyway, so to take away lots of matrix multiplication, but matrix multiplication is actually a lot of dot products, and dot products all take the same keys and query, or 2 vectors with the same dimensions, and just repeat it many times. So the prime candidate for parallelization, for using the GPU as a chip to design the chip specifically to support this kind of parallelization. So that's what we're gonna spend the rest of the lecture to go through some concrete examples. So okay, so next let's look at how we can code the matrix multiplication on a GPU. So well, matrix multiplication sounds scary, but if you see it as a larger dot product, so that's what we can focus on. Let's go to the basic. How can we calculate dot product? There are a lot of them. So we start with 1. So this is the format I use. So I actually like this so much that I use it in my AI by hand logo in a lot of places to show you that this is a way you could calculate dot product in this, and you meet here, and then can implement is as a maximum application. So let's just do slowly how to do this. So 3 times 1 is 3, 2 times 5 is 10, and 4 times minus 1 is 4, minus 4. So if you add these three numbers together, what is it? 9. Is it 9? I hope it's 9. Okay, and then if not, laugh at me, please. So if I do maximum multiplication, implement this. So hopefully, yes. Okay, I'm not hallucinating. Okay, so this is logically, if you calculate the math, maybe in a mental map, you could actually see that this is how you could arrange the tensors. But in the physical world, when we actually run this on a chip, so that laid out more like in the array or memory. So this is a better mental model when you actually move down to the physical layer. So when we lay out this number arranged in the memory, so I was just gonna refer to this one. It will become pretty flat like this. So I'll do a transpose and to do this one, so I can let it out. And somehow I want to compute C and then put it here in the next location in my physical memory. And so down, even inside into a core of a GPU computation unit, so there will be a very rough sketch. There are some registers. You will read memory data into the registers that have two registers called P and Q, another register to hold the result. So I just use three of them to show you in the hardware how this can be done. So first of all, I'll load 1 into my first register, this number, and I'll load this one into the second register. And then I want to perform the multiplication, add to the accumulator with plus and minus. So plus equal. So this is 3 here. And then next, I'm going to load this to number 5 and another number 2, and then multiply them and add to the accumulator is 3, right? So it becomes 13, okay? And do one more time, minus 1 and 4. So load this, read this, minus 4 and minus, get more 4 minus 4, and add to this, we get 9. Okay, so that's how I compute. I just emulate how a GPU core might compute in this way, and step by step. But we can also, next, we can actually do it, repeat this process by actually code this up. So you can see that. So I'm going to do is this, move over here, and this is this one. Oh, not this one. Sorry, this one is this one. Okay, and then I do is this times this. Okay, repeat this just to replicate a computation here. And this is, it seems like how it's so tedious, but this is a good way to kind of learn for you to internalize how the memory and read operation can move at such a low level. So this one I'm going to do is this times this plus the previous value here. Okay, so now 13. And now I can do one more time here, minus 1. This is going to read 4 into my another register. And I'm going to do perform multiplication between these two numbers and add to the accumulator, which is the previous value. And then I get the result. And then this is interesting. And I'm going to say, oh, I want to move back here. So this is the write back into our memory. Okay, so then so this is an emulation of how the process work, how that this actually can be computed. All right. Okay. Anyway, so this is how to calculate dot product. And we're not really talking about GPU yet, just like how you would compute the dot product in a sequence of operations. And you can start to see that there's a repetition here. So this is a repeatable, these are a sequence of 3 steps repeat itself 3 times. They're exactly the same, but they operate on a slightly different offset of your memory location. So what if I can rearrange them in this way? And you will just, and if I have somehow we can, so I just copy and paste, move them. So ideally, if I have a way to, oh, sorry, do that 3 times, let me just do slowly. I'm gonna cut this and move here. So this is how I was trying to emulate the parallelization. So if it goes through time, instead of time 1, 2, 3, what if I have three different threads, T1, T0, T1, T2, to do that in parallel. And they are in lockstep, meaning that every single step is they are doing exactly the same by a different offset. But if you are able to do this, it means that you could run that in multiple threads. That's what I'm gonna do next in more formally, okay? So let's go to this section, actually doing the multi-thread measure modification. So I have, in this example, I break down the same measure modification more just one element at a time. But here, what if I would like to repeat this measure modification between A and B about 3 times? So here I have not just B1, I have B2 and B3 in my logical space. I have two more B now. Oh, I want to take dot product between A. So this is the equation we had earlier. So how do we fill in C2 and C3? It turns out it's actually that simple. All I have to do is just extend this over here. So I get the three numbers. Okay. So, well, again, I try to show you that measure multiplication is dot product, many dot products. Hopefully, if you don't remember anything else, this all you remember today. Okay, so then I could do the physical memory. So via type F2, I can see that this is come from here. So I can repeat this, copy. I can repeat this. I go into transpose to lay them out in the physical memory in the 1D array. I do transpose again, and then for B3 over here, okay. And then I have 9 here coming from the equation earlier. I can already move back. And how can I compute C2 and C3 at exactly the same time? Okay, it turns out, so these are the equations. Just review this equation here. Okay. All right. And then if I copy all this to the right, okay, so and then almost so so that's almost right. Here, this is right. If you can examine it, whether it's selected the right location in the B2, but A1 is actually not correct. So I just fix A a little bit. I just move my selection to the left a little bit, and A, and move my selection to A over here. A, so in this you can see that A is referring to the same A, but oh, I forgot to mention, so we have thread 0, thread 1, thread 2, like 3 different threads, and I can copy the computation over, except that I have to adjust my A a little bit, make sure I select the right A1, this one. I think this one is incorrect. But how come I get 16, 26? Oh yeah, this 26, that's correct. Actually matches this comp. Yeah, this matches. Okay, that's correct. And now I have to do this one more time to fix my A. So this exercise is actually has a point. It's not pointless. The point is that this is how, when you actually get down to the CUDA programming layer, you're trying to figure this offset a lot. So Excel is an underrated tool for you to analyze this memory offset movement even at a low level like this. So anyway, so now I match -9 to my correct answer. So I could do is then I'll move my memory over here, and I move my result over here. Okay, so I complete this, and then exactly the same 3 times, and I all point to the A offset. Okay. So another way to do that is that if I just delete it and do it another way, what if before I copy, so I already know that my A gonna stay here, not gonna move around. And the Excel, the offset is actually F, the column is actually F. So Excel has a little trick that you could fix this, add a dollar sign to fix this, add a dollar sign to fix this. So this is CUDA equivalent of doing this sort of operation, but fix this. Once I fix that, so I can copy the whole computation over to T2, they will just work correctly as well. So I don't have to fix it. So it's all pointed correctly to A, but for B, it point to the B3 for each element. Okay, so this is like a reasoning that you can emulate at the Excel level. So I just performed this 3 different threads, but they are following exactly the same logic operation to complete matrix multiplication in multi-threaded scenario. Hopefully, so far so good. Um, how are we doing right now? we got a lot of questions, and I think they are doing a really good job of helping me answer this question. Okay, cool. Let's move on to the next step. Got turning back. Oh, wait, this was pretty cool. I can see we can run this multi-threaded, but I want to just purposely say, hey, what if I want to do single thread? I only have one CPU. So, and then basically I would just emulate this. So instead of running 3 parallel threads, I just put that into one long sequence. So this is just to remind us, what I'm doing is cut and paste this computation. So you could see that if this duration is time, so it takes 3 times more to go through the same matrix multiplication here. Okay, does it make sense? Hope that makes sense to you. So that is a comparison that, so if you now you can compare this section of the computation. Can you help me mute? Someone is creating background noise. Thank you. So that is much, much longer. Okay. All right, so now I'm gonna get it more technical. And how, so in here, I actually took advantage of Excel built-in offset. So when I copy computation, they will just take care of all the offset. And so using that as a background, and when you actually want to program in CUDA, so what's happening right now is that, so this is the computation I map out by hand. So you can see that for all A0, for all 3 threads, all point in the right location. And here, also point in the right location. So here, point in the right location over B1, B2, and B3. So now I want to actually write code to do that reference. So I want to match 3, 4, 2. This what number I want it to be 2. So this number I want it to be 1, okay, to match it. So this is my ground truth. So this is my when actually write it. So I have actually, I thought it's pretty hard, so I actually have this equation written down here already. So what this formula does, I'm copy the formula over here, is that, let me just rewrite this formula. So I want to let TID, which is my thread ID, and I have thread ID over here. And then, and actually, let thread ID equals this particular thread that received the ID here. This is my thread ID, and A is my A matrix over here. And then I want to compute the offset in such a way that this is rows which I can ignore, but this is where the column I need to be. So this is, in this case, actually it's 0. Okay. So if I do 0, I will actually can do this. And if my 0 is actually have another index j, so my 0 just use j here. So j is 0. Maybe, can I say j? Maybe use j. Introduce a variable j, and to be it's hard to select here. Select here. Does it make sense? Okay, here. And then I'll be able to use, I've use the j over here. Okay, I somehow somebody annotate my screen. Let me just delete it. Clear. Okay, so now I get this working, and I can do something similar for here. See if I can get 5 here. So I copy here this thing. I have to fix that. It has to refer to this one, and my j is referring to the right one. Okay, now I match. J is actually here, and I'll do one more time. This computation. Fix this a little bit. And now we have -1. Okay, it matches my ground truth. So this is a little bit more complicated. I like this value to select this one, this to select this one, and this to select this one, and so on. And so I will just copy my equation a little bit here, but I'm going to refer my B to be, delete this, to be the beginning of the B matrix here. I will still have my J here and J, and then and I want to calculate the right offset for B in order to refer to the element I want. So this is J equals 0. I just filled it out, so they all have access to the index J, and here is still not quite because I want this number to be 2, okay? Because 2 is here. So how do I get 2? Actually, I want this number to be 3. So this is a number I need to hit because I'm currently I want this number. Okay? So the third array, first element of the third array, how do I get this? So I will kind of times 3 times 3, move 3 like 2 times in order to hit this value. So with that intuition, I will say, hey, maybe I should do 3 times 0. Sorry, 3 times 2 plus they might maybe get what I need here. Okay, so what is 3 times 2? 2 is actually the thread ID, so I can use my thread ID there. Okay, so I get this. And so I get 4. How can I get 4? Is it right? 4? Why am I not doing correct? This light coding is always kind of hard. I like this to be returning 2, but it's getting me 3, 4. Why is that? Oh, the TID, I did not select the correct TID. TID is here. TID is actually supposed to be here. Okay, I did not select TID. Okay. Oh, so I can actually fix this. Okay, so TID is here. I think this is probably the toughest thing I'm going embarrassed. Now kind of make sure I select the right B, also right TID here, so I can get the equation right. But now I actually want to add 1 in order to select this one. And then copy one more time. Now I know the pattern. I fix this. This is B, and this is, so this offset is not entirely correct, but I do select my TID here. And then in this case, I'm just almost there. I have to do is add 2 here. And then if you observe the pattern over here, so this 1 and 2 is actually the value of J. So I could just do J here instead of 1 and 2. So once I do that, it's a pretty hard, but I still managed to do it in front of you without embarrassing myself too much. But I get to match my manual work. So manual results here, but this is a coded result. So once I feel pretty good about this, and then, okay, I think I figured out how I can program the offset. And you'll be ready to jump to what you could get paid a lot of money for, to be a CUDA engineer, to actually write CUDA code down here. So this is the CUDA version of what I just did, and a lot of this boilerplate, but I want you to focus on this loop. So we have this loop, and we remember we have J here. So if we can go back to this equation, no one see that for A, it's actually just J here, okay? And for B, it's going to be some kind of 3 times TID plus J, and 3 is my vector size, okay? Now we kind of do a pseudocode over here. So when I move down here, I can do exactly the same thing when I'm ready to fill. So this is AJ times B vect size. It's really hard to write. Okay. Vect size, which is a constant, times what? TID. His thread ID here plus J's. Anyway, I actually do not like my handwriting. One more time. Vect size times TID plus J. Is it better handwriting? I just do this 2 times for emphasis. So I'm just wrote CUDA by hand. And hopefully you could find a way to tie that into this tensor, like more like a transparent view of what's going on with all these numbers and about offset. So you could figure out the offset in Excel, then you can figure out the offset in CUDA programming. And it's just the beginning, first very critical step of understanding what's going on in CUDA. So, and basically you have this block of code, and they'll run on exactly the same set of they'll run the same code, but it just of a different offset using the TID, sorry, IDs, and so this is the to give you a taste of what how you will be dealing with CUDA. Hopefully that sort of makes sense. All right. So next, I want to talk about this idea of warp. So you heard of warp. So warp this term comes when you are trying to schedule a lot of threads on the GPU. So I have done this example scheduling three thread. We can imply there are three cores, 1, 2, 3 can run thread. I realize index is not consistent. What if we just use zero-based index here, 0, 1, 2? Maybe just fix it in real time. 0, 1, 2. Okay, so I have three core, and so we can run at least three thread. Physical limitations, three thread, but in reality, there's like thousands of threads, thousands of cores. But here, just deal with three. Okay, so a warp is a unit that you can actually schedule at a time. So I'm scheduling three at a time. And so if you want to do it in we have more beats now going all the way here. And the computation is the same. I just extended my matching application to like just more columns, more beats. And in this case, but in order to compute the entire matching application, we just have to, we can kind of do all this much at a time. So we just have to do more times. And then we call this like warp. So we have 0 warp, 1, 2, 3, 4. So we use W to indicate that. Okay. And the kind of interesting thing about this is because the nature of this computation is actually quite easy to emulate. All I have to do is copy, okay, and I paste over here. So the computation will exactly the same. It still work because I already do the trick of adding a dollar sign to fix my column. So they all refer to A. I just change to warp 1. Okay, that's done. Now hopefully you get I just did another warp. Now I can manually. So so the technically it's called A same but I just emulated what that is doing. Okay, now I'm just scheduling another one, warp 2, and run this. And now I can do it warp 3, and the fact that I copy and paste the whole thing just as to emulate how repeatable and parallelizable the computation is, and all based on figuring out the correct offset. Done. Now I just in front of your eyes, I schedule how many warps? 5 different warps to compute this large maximum location. And then if you want to do another, sometimes you might like to just sum all these numbers together. For instance, I will say I want to sum this, okay? And so I have to wait all the five warps are done before we can sum this number into one number. So we can also do the same thing here. We take the result, which is the last number, here. You can see it here. Okay. Now do the sum. Okay. And then just sum all the result here. And okay. So there's a sum, and then you can see that they are somehow all the communication need to happen in order to collect all this number to sum them. So that's called reduce. Okay, so or reduce into this one number, and you can simulate reduce in by this way. And I don't quite understand why I keep getting this. Annotate, delete, clear drawings. Okay. All right. So what I'm gonna do is I want to zoom out a little bit and see a bit more. I do 75% now. And then so I'll show you something really cool about Excel, that there's a way that you could, I look at the 20 right here. So I'm going to go to formula. I'm going to show trade precedence. If you use this feature, it's going to show you visually the computation graph where the number comes from. So in this case, 20 comes from the row of all these numbers, but keep pressing it, you can trace this. Then you can actually visualize this is in fact very parallelizable. So this is something, this is all you can divide anywhere you want. Okay, because, and you can also share that all share A, so then you can kind of see that, hey, A is kind of important. If you can somehow fix that in the memory, that might help. So that allows you to do the analysis. And then I will just go go to again, so it move up to the logical space. So imagine this is in your code in the CPU have this large tensor. So that's how you can see you have to load them in some kind of memory and that's the way that things are moved around. And then just remove all the arrow, then go to the next section. Now we are straightening all the warps. And then what does the block mean? Also, the block is even a bigger unit of warps. A block has lots of warps. And so we have this is block one. So now I add another row here for A2, but it turns out this is actually where you can get divided. What if I just divide all the computation for A1 to one block, A2 another block, and I could actually parallelize. And to do that, it's actually not that hard because this is a lot of repeatable maximization. So I want to simulate how to schedule another block. Okay, so I have one block done. All I have to do is copy. You can get an idea of what I'm up to. So what I'm doing is I just copy the whole computation, and then I move down here and just paste them in the space down here. And then, so I call it block 2. And I make sure this actually refer to A2 instead. So I'll fix this over here. Select here, okay? And then this one come from here. So in this exercise, you realize two blocks all have to access B. So you can visualize now this one, F2, you can see this and this here, but this one being also B, you need the B, but over this block, you no longer need to access A1 here. However, the computation is very repeatable. So you get this final result the same as you would have done here. So this is I measure using the maximum applications 11, 12, 11, 6 here, right? But if you do another block of this, you get exactly the same computation to show you that it is possible. Okay, and then we'll still have this summary here. So what if we do another reduce here? I just going to sum all this. This add, sorry, not what I want to do. Okay, I'll use my keyboard. I'll select this one plus this one. So now all the computation will flow, eventually merge in this number. I did it on purpose because I want to show you even nicer graph. I'm going to change my resolution to 50 so you can see even more now. Okay, and then I'm going to do that trace precedence. And then now you can see the computation go in 2 ways and go back up. And this is allowed to see that you really talking about 2 very separate computation paths here. So you can draw a line sharp right here. And anything that's happening here and happening here, that could just happen independently because no interdependency between them. So there's another way for you to eventually to understand that in terms of the block, and none of this computation need to access memory. So they all have their own memory access. They don't have to access each other's memory. So that's why, but all the warps, all this along here, you have 5 warps, right? They all access A1. They all have the need to share memory between them within the block, but not between the block. I hope it makes sense. One more time. There's memory access, share memory access within block, but not between the block. Hopefully this visualization help you actually see that, get better intuition about that. Okay, all right. Next, let's just now we're gonna move on a different topic about quantization. And so they get into like large language model and then we have these billions of parameters and then realize, hey, I really just, as much as I can, I harder how to fit into the memory. What if we can use less memory to represent the same number? So this is like idea of this very active research area and also become a well-spread engineering practice for quantization. But I want to help you build some intuition about what really means by when you quantize and what does it mean when you actually work with GPU and how GPU got redesigned to do that. Hopefully enough time to just give a good justice to this topic. So this I prepare the integer 8 format in bits. So this is the binary format with 0 and 1. So I have a binary to the decimal to show you that is how this is actually 36, okay? And if I turn this one, it becomes 32, and this becomes something other number. So this is, and then this is but it's very hard for you to build intuition using the binary number. So I invented another data type called decimal 8. So this is still eight different things, but they can be going from 0 to 9. So but it's just like mapped to the decimal number 1, 4, 1, 2, 4, 1, 2, 3. You see this? And every launch you see here is applicable to binary format here. But now, but I want to just show you this side-by-side comparison. So we have decimal, we have integer, but the quantization, dequantization, the concept is whatever you see today for decimal is equally applicable to integer. Okay, just want to establish that first. And I'm going to show you that I do have this all connected together. If you change this number, you can see that this 5 different separate number being combined into 50215. So that can visualize the effect of this representation. So okay, so now we're gonna go from this concrete example. How do we go from code to memory? Okay, and to cores and memory, and run through with in the format. This is the case of with before quantization, but I want to show you have a lot of numbers here. A is at 4 different vectors, and B we also have 4 different vectors here. And the code is that I want C to be the result of A plus B. And then you can see that this is actually 4 different vectors that can be parallelized because the element-wise adding, they are like the same across the same vector size. And so I want to load that into the chip. We have some register that can hold 8 digits, even though I'm living in the digit world, not like a binary world, so it's easier for the reason, but the idea is the same. I want to load then back into register in the core. So I purposely lay in this way, but I have to do a transpose for it to fit. So this is how I'll emulate loading something from the memory into my register. And because if I lay this way, I can say, hey, I actually have different cores, eight different core, but I only use the 4 core to hold 4 numbers, 4 vectors on the A. I'll do the same thing for B, transpose B, and this, and then this, and then we'll take this number. And then inside of the chip, so I can take 2 registers to add them, and I will do addition, I emulated parallel addition. So I select everything here, and plus I select everything here, so they can be all done in parallel. And we can get this new set of vectors. They are the result of adding these 2 vectors, but we have 4 such vectors being added on 4 cores at the same time. So because that's how we do multi-thread programming, I did this way, as we showed earlier in the example. And now we can load that back into my memory. So I'm going to do transpose back and take my result here. The reason why I'm doing this is I want to show you how we can do the same thing, but in a with a quantization. Okay, so now this is a normal flow of going from code to memory to the cores, and when the computation is done, load back to the memory. Okay. Anyway, let's do that. Next is to show you quantize and dequantization process. So the quantization is we have this number. I want to use half of the memory storage to store this number. So one way is that I just pick, I could just simulate quantization to find, hey, I think maybe I select this 4 digits can give me the best. This is basically what we do, is select this. The reason why I don't select this is because I have some 0. I'm wasting my storage for the zeros. So I think this, but if I select here, come on, that's not what I do. What happened here? Okay, if I select, had I select here, I can lose too much and the higher number here. Anyway, so I have this. This is basically quantization in a nutshell. Now I have the deck 4. And if I dequantize, I will just add those and load this back here, but I don't have this information anymore. I just fill this up with 0. So this is the process of quantize and dequantize. You can emulate by hand. And so you can compare these 2 numbers. You can see that you have that 1, 2, 4, 1, 2, 3, but you're losing the 1, 2 lower digit number 1, 2, 3. Actually, did I make a mistake? Oh, sorry, that's not what I'm doing. I go back what I'm saying. Okay. I realize I skip ahead a little bit. So what I'm doing right now is that, and this is a regular quantization, is that I just take the top 4 digits here. That's what I'm trying to do. And when I get it back, I'll just take the top 4 digit here and append a whole bunch of zero here. Okay. So I forgot what I just please forget what I just said because I skip ahead. I just explains the mix format earlier, a little bit too premature, so it might be very confused. So let's do this example one more time. If I take the first top 4 digit, then I only have this little one here. When I reconstruct, actually I lose a lot of number. I want to use this example to illustrate the even though quantization help you save space, you're also uh, losing precision as a result. So now everything, many of them not surviving. Only the third vector is survive. Everything else be set to 0. And so the next example is what I want. What I okay. Actually, my next example is to show you after you dequantized, the computation on the chip become like the chip was designed to still hold 8 digit, but in the memory you can actually store less using less memory to store. So I will still do my transpose with my A, and then I'll get another transpose and transpose. Because memory, the chips that we have this 8 digit chips, and we're not using a lot of them. These are unused space, but the point is that I can use this memory less, so I can store a much larger model on the memory, and so I can still perform my addition simply by taking this whole thing, add this, okay. And then we'll load it back here, but I need to only load the first 4 here. So, and this is how I emulate with a traditional GPU, use GPU as is. You have dequantize this way, dequantize this way, and quantize back in this way. And then how you can exchange data between memory and the chips. This is what I want to do, the how to preserve details from squeezing. I skip ahead a little bit to talk about the logic here. So the logic here is that I want to select just the right amount of precision, but I can store where my exponents are. This case is 3 here, okay? So I store this and remember, hey, I'm taking my top digit from position 3. I can do the same thing here, and now I want to select here instead, okay? But I can keep a lot of details. But in this case, my exponent here is 1, so I can store it this way. In this case, and then when I bring them back, I remember this is 3, so I can just put it back in the right position. I also remember this is 1, so I remember I put in this position. And then you can see that, and the actual number is actually preserved. We still get 1120 out instead of 0. In the earlier case, everything became 0. But in this case, it's called mix MX. You heard MX, FP4, FP16. MX means this mixed precision. So we can have the same quantization, but mixing the precision in this case. Okay, so MX, I will call MX4 because I use decimal number to illustrate. And that's pretty cool because once you do that, you can also implement this on chip. In my next example, what does it mean when we each run on the chips? Do I have time? Yes, I do. Quickly finish this on the chip side. So I will be able to do is that when I dequantize instead of loading over here, because I know this is exponent is 3, so I can load this. I still do transpose, load this here at the right exponent. And then this one, I can load it here, transpose. Okay, transpose here. And then when I use just existing chip to just add them in parallel, so I'll just add the whole thing plus this whole thing. and then I get the result I need. So I can select, hey, I think this is the best here, right? So I'll go select 3 here. I will already put 3 here. So I do transpose. So I actually simplify by not working on thinking about carry and so on, but just like, so this is a principle. I could use mix precision and do some clever CUDA programming to implement this using the existing chip design. And as a chip maker, like NVIDIA or some other maker realize, hey, the machine AI engineer really want to do this. They started to think about what if I just add that directly into the chip? So I could save a lot of this computation. These are unused computation and space, on the core. So what if we just make a smaller core to support its mixed precision? So if we do that, this is my last section, we can actually provide native chip support on that. So when I move data in, so I can move in the more compact space in my register, and then somehow find a place to store this 3. And then I also do a transpose. I know this is grossly simplified, but I think I still offer enough of the detail that to allow you to see this. Now I can do addition as we did before, but there's no wasted space. But actually, in this case, before I do that, I have to actually just move these 2 over here, because the offset is actually 1, 3 and 1. There are 2 spaces in between. So I just take the first 2. So when I add them, I will just add this plus this, and now and then the precision, the exponent is still 3, and then I move them back. So hopefully this computation is a lot more compact, and it seems like if you see this small example, the change is not that big, but you're thinking about billions of parameters trying to multiply in many, many times. So that the saving is actually pretty significant. Okay. All right. So this actually all I have. I did manage to stay within my time limit, and I get a tons of question in the chat, and I think that Zhang and Shangya are doing a good job supporting your questions. But please send us questions if you have this, and we'll share the solution, also recording afterward, and then I'll also review the question in the chat later. But I would like to have Zhang back and to properly close this section.
Awesome. Thank you so much, Tom. That was awesome. So I was interacting with folks in the chat this whole time, and really great questions. Um, I think a session like this kind of gives us. I studied all of this back in university, and now that we're kind of programming on top of this, you tend to forget that at the end of the day, it's very simple matrix multiplication. You know, you've got all of the complexities of real life, where you're kind of distributing and making this thing go as fast as possible, organizing and scheduling so that you're making sure that you're using the GPU at maximum utilization all the time. But at the end of the day, it's simply matrix multiplication, and we're just trying to go as fast as possible. Yeah, I think this was awesome. And if people want to check us out, one interesting thing that I recently did is Karpathy released NanoChat, and I was just playing around with it. And so I released a guide around it. If people want to play around with it, you can go ahead and use instant clusters for that. If you want to use any new models, feel free to give it a try. If you have any questions for me about Together or any of the work that I do, feel free to reach out on my social media platforms. I'm happy to chat with anybody. And Tom, thank you so much. This was
Thank you.
awesome.
And just a quick plug. So I'll do another keynote like this sponsored by Vectera in November, and there will be on hallucination. If you wonder how the hallucination happens, so we'll do similar style to break it into the black box. And next week we have a 20 years AI by hand workshop to go through the most basic stuff. The fact that you're here, probably that workshop too easy for you next week. But you have friends who always wanted to get into the math of deep learning. Next week is a good opportunity for our 20 years AI by hand workshop. Thank you, Zane. It's been fantastic. Thank you, Shangya. I hope that your fingers not too tired typing out all these answers. And we'll do this again. And thank you all for coming. And Shanya, do you say a final word before we close?
Yeah, definitely. I think it's just really helpful for more people in the industry to understand the math behind this, because then you can approach optimizing parts of the hardware intelligently. And that's what I'm trying to do at Micron as well. And this was such a helpful lesson. Just like some learners, Dr. Ye, I'm going to have to go back and rewatch this and redo this. So thank you so much for this
Okay.
opportunity.
Oh, thank you all. So until next time, bye bye.
Thank you. Bye.